Hello students, welcome to the lecture 2 of this week, in which we continue the review, and we're already in the second lecture of the review. The one little thing that I haven't finished in the previous lecture is the following definition. So we're going to define double inequality. If A, B, and C are real numbers, A, B, and C are real numbers, we will write A less than B less than C when A is less than B and B is less than C. So geometrically, it's really easy to represent. Geometrically, it just means if you have number A to the left, number B in the middle, and number C to the right. So we mean B is bigger than A, and at the same time, B is less than C. So that's one definition probably I should have included in the previous lecture, but it's familiar to you, it's just a review, so you kind of know all of these things. So moving forward, we have this new definition, which is saying that a set that we're defining in this definition is a collection of objects, right? Any kind of objects we can put here, and these objects are called elements. Sometimes people call them members. Of the set. So let's try to see what kind of examples would fit into this definition. What kind of examples we can put? For example, we can say all positive integers less than 5. So how can we write it? People usually write sets using curly braces. So open curly brace, then 1, 2, they have to be positive and they have to be integers. So it cannot be 0, so it has to start with 1, 2, 3, 4, but 5 we cannot include because they have to be strictly less than 5. And we close the curly brace, right? So curly braces tell us that this is a set. This implies this is a set. All right. What else we can do? We can we can put the set of all positive integers. The set of all positive integers. So let me ask you, how would you write it? To write it, we need to use a curly brace. We open it up, and they have to be positive. So we say 1, 2, 3, 4, but then they have to keep going, and we can't really write all of them down because we will run out of space. And as you remember from the previous lecture, if you want to say that something keeps going in mathematics, you use 3 dots, right? And that's how you would write all positive integers. And what else we can put here? We can put the set of all positive even integers. So what we would have to include here? We would have to include 2, we would have to include 4, we would have to include 6, 8, and 3 dots means it will keep going. All right, so we gave few examples how to do that, but let's try to build up on this idea of writing sets out. So next idea, we'll put it this way. When it is inconvenient or impossible to actually list the members of the set, it is sufficient to define a set by stating a property common to all of the members. Common to all members of the set. So for example, we can say, the set of all rational numbers. Because we can't really list all of them out, but we can just write set of all rational numbers. So each number in the set has to be a rational number. Then what else we can say? The set of all real numbers x such that 2x squared minus 4x plus 7 is equal to 0. Then our set will consist of all of the solutions of this quadratic equation. Another thing we can do, we can say the set of all real numbers between -1 and 5. Again, it's really impossible to list them because there's infinitely many actually of them. So this is a convenient way to write. But for this type of writing, people created so-called set builder notation. So we can use set builder notation. So set builder notation is having this form. So the form is again curly brace curly brace at the end, then X, and some people use column, some people use vertical line. And after the column over here, or after the vertical line over here, we have to state the property. We have to state the property that specifies the set. All right, so we put this property over here or over here, because some people again use column, some people use vertical line. So how do you read it? You read it as the set of all x such that, and then you put what the property says. All right, so basically this part says the set of all x such that, and then the property has to follow. So let's rewrite the assignments from previous example in the set builder notation. So part A was the set of all rational numbers. The set of all rational numbers. So we can say x such that x is rational. So x satisfies the property that it is a rational number. Part B, what did part B say? Part B says that the set of all real numbers x such that it's a solution of this quadratic equation, 2x squared minus 4x plus 7. 2x squared minus 4x plus 7. So x such that 2x squared minus 4x plus 7, I think, is equal to 0. Right? 2x squared minus 4x plus 7. That's correct. And part C, what does the part C say in the previous exercise? The set of all real numbers between -1 and 5. So we can just say x such that x is bigger than -1 and smaller than 5. So this would be the set builder notation. Set builder notation. All right, so just a convenient way to build sets when you can't really write it out. So a couple small definitions that we're gonna need. So first definition says that to indicate that an element A is a member of the set A, or maybe of a set A, we write A, then special symbol A. So how do we read it? We read as A is an element of A. And the opposite of being in the set is not in the set. So we can say that when when A is not an element of A, we write A is in set A, but then we cross in with a line, and that means it is not in A. All right, so you read it as A is not an element of A. Or some people say A does not belong to A. All right, so let's look at some examples. Some examples would be, so first we're going to define the set. The set A will have X such that X is rational. And set B would be X such that X is between 2 and 4. X is between 2 and 4. So let's try to see what would be in A. Like 3/5 will be an element of A. -5 will be an element of A. But number square root of 2 will not be an element of A, since square root of 2 is irrational. Or number pi, which is also famous irrational number, is also not in A. All right, but what would be in B? Like number 2.5, it's bigger than 2 and less than 4, so it's going to be in set B. Number pi will be in set B since it's 3.14, so it's again between 2 and 4. But -1 will not be in B because -1 is smaller than 2. And 4 itself, which is a borderline of the set, will not be in set B because it has to be strictly less than 4, but we have a number that is bigger than 4. Sorry, which is equal to 4, but we cannot really include it. Another idea that I would rather include in this video lecture is an empty set. So another definition that we're going to need is empty set. Empty set is a set that has no elements. A lot of people call it null set. Some people say it like this. So what would be an example? For example, if you take all x such that x squared is less than 0, it's not going to be possible, because if you take any number and you square it, it's at least 0 or bigger. Like 0 squared would be 0, but everything else squared will be bigger than 0. So this set wouldn't have any elements, and so this would be an empty set. But mathematicians always use some kind of a symbols. So the symbol for the empty set is a circle crossed with a line from right to left diagonally. So this is a symbol for the empty set. So probably it's a good place to stop this lecture. This was lecture 2 for this week, and I will see you in the next lecture.